Hello everyone, this is lecture 3 of course PE 645. In the previous lecture, we have covered the radiomics workflow with artificial intelligence, and we mentioned that it consists of mainly 6 steps, it can be less or more, from acquiring the dataset, segmenting it manually, extracting the feature, applying pre-processing, developing the AI model, applying explainability at the end, reporting high-performance metrics and explainable model, so we can say that we can trust this model. We also mentioned how to extract the first order features from simple matrices, 2D images, and 3D volumes. These first order features are grouped and categorized under the first order features. So, what was the difference between first order, second order, and higher order? Simply, it depends on the complexity and relationships. First order features directly deals with the pixels themselves, such as getting the standard deviation of the pixels, and there is no relationship between the pixel and the neighbors. But in second order features, there is a spatial relationships between the pixels. So the current pixel has a relationship between the neighbors, such as GLCM, Gray-Level Co-occurrence Matrix. And we are going to deal with this in this lecture. Higher order features depends on complex mathematical transformations or filters applied to the image. And the aim of capturing all of these features is to describe the distribution, texture, spatial relationships, shape, and so on. Based on that understanding, we can develop the AI model. That AI model can discriminate based on these features on the different categories, such as being benign, being malignant, and so on. So let's start with second order features. One of these second order features is called GLCM, or Gray-Level Co-occurrence Matrix. And GLCM analyzes spatial relationships between pairs of pixels. And this relationship is considered a second order statistical operation. Again, first order features deals with the individual pixel values. But in GLCM, it examines how often specific pairs of pixel intensities occur at defined distances and angles within an image. And we will illustrate the meaning of this sentence after a while. The GLCM was introduced in the 70s by Harlech and Shanmugam, where again GLCM quantifies the frequency of pixel intensity combinations. It's called the Gray-Level Co-occurrence Matrix. So the meaning of Gray-Level is that we are referring to the pixel intensities in a grayscale image. So when we are going to deal with images, we are going to deal with images that contains grayish pixels from 0, which is black, to 255, which is white. Again, this image is called 8-bit image. And co-occurrence matrix, in the definition of GLCM, is to analyze the spatial relationships between neighbors by quantifying how often specific intensity pairs occur. The benefit of the GLCM, it captures the texture patterns by examining the arrangements and co-occurrence of pixel intensities within the image. To understand all of that and the meaning of the occurrences and how often specific intensity pairs occur, let's start by defining 3 key parameters for the calculations of GLCM. The first is the distance, and the distance here is the displacement between 2 pixels. So if you have an image and there is a pixel here and the neighbor is here, so the distance is 1. And if the pixel is the target and this is the current, then the distance would be 2. The second parameter is the angle, theta. This is the direction in which pixel pairs are evaluated. And usually we use the angles 0, 45, 90, and 135. The third parameter is number of gray levels. And this is the number of discrete intensity levels. For example, if you have 5 unique values in the image or the matrix, then n will be 5. Now, after understanding the meaning of each parameter, let's understand the meaning behind the co-occurrence matrix. Let's assume that we have configuration of distance of 1, theta of 0, and number of unique pixels is 4. And I will tell you after a while why it's 4 for now. And this is our matrix. If you notice in this matrix, it's 5 by 5, 5 rows and 5 columns. And if I asked you what is a discrete unique intensity pixels here or intensity values here, you would say 0, 1, 2, and 3. In this case, I will ask you to count them. You will say 4. And that's why in this case equals 4. So you determine the value of n based on the count of unique discrete values in the matrix. But the distance and theta are predefined, and you can change it based on the complexity you need or the scope of the analysis, or you can capture multiple configurations and compare between them. But for now, let's assume the distance is 1 and theta is 0. We mentioned from a while that the co-occurrence matrix is the spatial relationships between neighboring pixels. We mentioned from a while that co-occurrence matrix can be achieved by quantifying how often specific intensity pairs occur. Notice here there is pair. Pair means current pixel and the neighbor pixel. How often means the frequency, how many times. So to build the co-occurrence matrix, we need to apply that on our matrix. What is the aim? The aim is to build a matrix called co-occurrence matrix. What's after? We need features. So based on that co-occurrence matrix, we will get the features. So we will extract the features based on the co-occurrence matrix, not the original matrix. So in second order features using GLCM, the steps are: first, create a co-occurrence matrix. Second, extract the different features from it. Because by the end we need numeric features, such as the features we extracted from first order. So let's start by building the co-occurrence matrix. First, create an empty n by n matrix, and n here is this number. So the size would be 4 by 4. And it's recommended that to put the discrete intensity values beside each row and above each column, like what you see here. This placement will help us to place the values inside the matrix. What's after building the empty matrix? We need to understand the meaning of distance 1 and theta 0. For the angles, you start by the right side horizontally, and if you need to increase the degree or the angle, you go counterclockwise in that direction. So 45 is this angle, 90 is this angle, 135 is this angle. What about the distance? The distance is how far the target pixel and the current pixel. So if I said that this is the current pixel and we have a distance of 1, then the neighbors will be this one, or this one, or this one, or this one, this, or this, or this. What determines which neighbor is the angle. So at distance 1 and the angle 0, if this is the current pixel, then the pair of this current pixel will be this pixel, because we need to look forward the direction. What about this pixel? At the distance 1, theta equals 0, this will be the neighbor. What about if we have different angles and thetas? Let's assume distance at 2, theta at 0 is the current pixel. So at distance 2 and angle 0, which is this direction, this will be the target. What about 45? We mentioned 45 will be this direction. So this direction. But we need a distance 1, so this will be the target if this is the current. But you may say that after a while we are going to script that using Python or any programming language. So how can we tell the programming language that based on that angle, based on that distance, that this is the current and this is the target and so on for all of the different pixels? Simply, you can use these formulas. The target is equal to the current plus rounding the distance multiplied by cosine theta if you need x-axis and sine theta if you need the y-axis. So let's substitute in this one. Let's get x. So the x target, we have x current, which is 1, plus the rounding of 2 multiplied by cosine 0. Cosine 0 is 1, multiplied by 2 is 2. So rounding of 2 is 2 plus 1 equal to 3. So the target x will be 3. What about y? Y is 1 minus, follow the formula, round of 2 multiplied by sine 0. Sine 0 is 0, multiplied by 2 is 0. Rounding of it would be 0. So 1 minus 0 is 1. So the location of the target will be 3 and 1. If you apply it here, the angle is 45. So cosine 45 multiplied by distance 1, which is that one, is 0.707. The rounding of it would be 1 plus the current x would be 1. So the value would be 2. Sine 45 is also 0.707 multiplied by 1 is 1. 1 minus 1 is 0. So the target would be 2 and 0, which is this one. And these are another 2 examples. You can pause the video and validate the results. To recap what happened, first, we mentioned the meaning of GLCM, Gray-Level and Co-occurrence, and we mentioned that we need 2 steps. The first step is to create the co-occurrence matrix. The second step is to extract the features from that co-occurrence matrix. The co-occurrence matrix, to build it, we need 3 parameters: angle, distance, and n. N is calculated automatically by finding the count of discrete unique values. D and theta are predefined. Next, we understood the meaning of the angle and distance, and by changing the values of them, we can determine easily using the 2 defined formulas the target locations based on the current locations. We also mentioned that it's recommended to place above the columns and rows the unique discrete values, and this will help us to build the co-occurrence matrix. So after understanding these concepts, now let's begin by filling the co-occurrence matrix using distance 1 and angle 0. So if this is the current, this would be the target based on the formula or based on the angles chart here. Again, we placed here the unique values and also here for simplicity. And how can we fill the co-occurrence matrix? Simply loop on each pixel and find the neighbor, and based on these 2 values, increment the cell where the current pixel is the x and the target pixel is the y. What's the meaning? Simply, if this is the current location, this will be the target. So we have x equals 1 and y equals 2. So go in the co-occurrence matrix and at x equals 1 and y equals 2 and increment that field by 1. Then move to the second pixel. So the next pixel will be 2 because, as mentioned, we are looping on each pixel value. So the neighbor will be 3. So the x-axis will be 2, y-axis will be 3. So at the location of 2 and 3, increment that field. At location of 2 and 3, increment that field. So we will refer this by x-axis and this by y-axis. Next, 3 and 2. So at 3 and 2, increment that field. Move to the next pixel. 2 and 1. At 2 and 1, increment that pixel. What about here? If you encounter that the location of the target pixel is outside the boundaries, then ignore that pixel. So in this case, we will ignore this pixel. What's after completing the first row? Move to the second row. Now, let's start by this. So at 3 and 1, 3 here, 1 here, so increment that field. The next is 1 and 2. At 1 and 2, there was 1 here, and we need to increment that field, so it will be, in this case, 2. What about 2 and 1? 2 and 1, increment that field. It was 1, so in this case, it will be 2. You will continue until you reach the last pixel, which is that 1, and that pixel will be ignored in that case. And by completing iterating over all of the pixels and filling and incrementing the co-occurrence matrix, you will get a matrix that looks like that. If you encounter that a cell is empty, fill it with 0, like here, 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 and here. So the operation is simple. Get the current pixel and the target pixel. The current will be the x-axis. The target will be y-axis. Fill the co-occurrence matrix by incrementing the cell of x and y by 1. Loop on each pixel until you reach the end of the matrix, and this will be your co-occurrence matrix. This co-occurrence matrix can be called normal or traditional or standard co-occurrence matrix. There is another co-occurrence matrix is called symmetric co-occurrence matrix or symmetric GLCM. How to calculate it and what is the difference between symmetric and the traditional or non-symmetric? Let's start by how to calculate it. First, after calculating the traditional one, apply transpose by swapping all columns to be rows and vice versa. So this row will be column, this row will be column, and so on. After that, sum both of them, the original and the transposed matrix. Simply, 0 and 0 will equal 0. 2 and 0 will equal 2. For example, 3 and 3 here will equal 6. 4 and 3 will equal 7. Do that for all of other cells. You will gain the symmetric GLCM co-occurrence matrix. What is the differences between the normal and symmetric one? Simply, normal GLCM provides detailed directional analysis, and it's essential for textures where the direction is important. However, in symmetric GLCM is more generalized and simplified representation, and in this case, it captures the texture regardless of direction and orientation from which they are observed. So, if we compare between them regarding directionality, it's observed and retained in normal, but eliminated in symmetric. If you need features that depend on the direction, so use normal, but if you need to ignore the direction, which is the direction of theta, use the symmetric. Now we need to script how to calculate the symmetric and non-symmetric co-occurrence matrices. But before going to illustrate how to code that, let's recap what happened. First, we understood that we need two steps. Create the co-occurrence matrix, extract the features from them. To create the co-occurrence matrix, you need three parameters: angle, theta, distance, d, and unique discrete values, n. Create an empty matrix equals in size of n by n. Start filling it. How? Simply iterate over each pixel, get the pixel, find the neighbor based on the angle and distance, using the current pixel value as the current x in the co-occurrence matrix and the target as the y. Increment that cell, complete the iteration over the matrix. Now we have a co-occurrence matrix. If you need the symmetric one, transpose the original, sum both of them together, you will gain the symmetric co-occurrence matrix. Go to the script called GLCM co-occurrence matrix example. In this script, we are going to create a co-occurrence matrix based on a simple matrix, like what we did with the first order features. First, we imported the necessary libraries, such as numpy for mathematical operations and plot for plotting. Then, we define the different parameters: d equals 1, which is the distance, theta equals 0, which is the angle, and define the angle here in degrees. Then, we defined a parameter or a flag. It's called a symmetric. False means no, true means it's symmetric. Then, we defined a matrix, a list of lists, and each list defines a row. And this example is similar to what we calculated using hand calculations in the slides. Then we converted the matrix, which is called A, to a numpy matrix or array for better manipulation. Then initially we printed the matrix. So after executing the code, the matrix will be printed on the command window. So let's start. So there is a missing parameter, which is n, and we mentioned that we can calculate it automatically. How to do that? Simply calculate the minimum value, maximum value, subtract both of them together, and increment 1. So the minimum can be retrieved using a function called min, and the maximum is retrieved using a function called max. N equals max minus min plus 1. In our case, the minimum is 0, the maximum is 3, so 3 minus 0 plus 1, n in this case will equal 4. And this is correct. Another example, let's assume this example. The minimum value here will be 1, the maximum value will be 6. So 6 minus 1 is 5, plus 1 is 6. Let's count the unique values. 1, 2, 3, 4, 5, 6. We have 6 unique values. So simply find the maximum, subtract the minimum, and increment it or add 1. We mentioned after getting the n value or defining the parameters, we need to create an empty matrix. So we created an empty matrix n by n, filled with zeros, and we will refer it as co-matrix, which is the co-occurrence matrix. In this step, we converted the angle from degrees to radians. Why? Because the cosine and sine that we will use later in the loop to determine the target location requires the angle to be in radians. So we added this step. Now let's iterate over each pixel value. So we got the shape, and we mentioned that the shape is the size of the matrix. Here we are getting shape 1 and shape 0. What does it mean? Simply, if we have a shape like that equals rows and columns, so shape of 0 is rows, shape of 1 is columns, because Python starts with the index 0. So here we are looping on through the columns and rows. In each iteration or in each inner iteration, we will do a set of steps and then increment the value of the co-occurrence matrix by 1. First, we will get the current location, and we started by the y location, as the matrices in NumPy starts with the y location. So we define here y location, then x location. But in your hand calculations, you start with x location and y location. Both the results will be the same, but here we defined y first to match on the way NumPy arrays are defined. Then we use the two formulas to get the target location by simply d multiplied by the cosine, use the round function, and add the current x location to get the x start. The same for y, but here sine and here minus. Now we have the end location, y target, x target, and we convert it to integer because accessing the indices requires the value to be integer. So 9.0 is different than 9 in accessing the indices. So to ensure that each value as to accessing the index is integer, we use the function here integer and here integer. After that, we checked if the end location, which consists of the y target and x target, is inside the boundaries, then we can continue. Other than that, we will skip that pair. So if it's outside the boundary, we will skip this iteration and move to the next pixel. Now we have end location, start location. We check that end location is inside the boundaries. Now we need the corresponding values from the original matrix. So to simplify this, we mentioned in our example that we have current pixel value and target pixel value. We will get these pixel values. So how to get these pixel values using Python? So simply we can define a variable start pixel and end pixel. Start pixel is the one with the start location and end pixel is the one with the end location. And we subtracted the minimum value from that value and from that value, so it can work with the different matrices that doesn't start from 0. So this is a technical step that ensures that it can be filled correctly in the co-occurrence matrix or the different matrices, especially the ones that doesn't contain or start with 0. Now we can change that value with the start pixel and that value with the end pixel. And if you look here, you will say this is the y because we start with y, and there's the x, and this is correct, like what we did with hand calculations. So here means increment that cell by 1. Get the previous value, increment it by 1, and set the new value. After that, we are debugging by printing a statement, start location, end location, and increment that field by 1. After completing the iterations, now we have a chance to check if it's symmetric, then add the transpose of the matrix to the original one. So if it's symmetric, find the transpose using .t, increment it to the original one. And here NumPy will perform pixel to pixel addition or pixel-wise addition. We'll get each corresponding pixels and add them together. Finally, we can print the co-occurrence matrix. An additional step, we can display and plot the co-occurrence matrix as a grayscale image. If you executed the code, you will find this output, which is here, and also a visualization of the co-occurrence matrix. This visualization doesn't have sense in this case, but it will be visualized better and will have meaning when we visualize a co-occurrence matrix for big image. And these are the steps. So simply, you can pause the video and follow each line of these steps and check each step of them. Did we do that using hand calculations or not? You will find that the script performs similar to what we did using hand calculations. So you can use that debugging in further applications. You can change the example, try to apply hand calculations, and validate that with that script. Now, this is another example. You can pause the video and try it. In this case, we have angle 90, which is this direction. Distance is still 1, and we have a matrix. So it's a similar example, but I changed the angle from 0 to 90. If you solve it, you will find that there's the output for the non-symmetric and there's the output for the symmetric. We built the co-occurrence matrix successfully using hand calculations and using the script. Now, we need to move to the second step, which is calculating the features. And these features, again, are calculated based on the co-occurrence matrix. So you need to ensure that the co-occurrence matrix is calculated correctly. These features include energy, or called angular second moment, in short ASM, contrast, homogeneity, entropy, correlation, and dissimilarity. The energy means the uniformity of the image. So the more energy is the more uniform texture, or the more angular second moment. The contrast gauges the local variations in the image. So if the contrast is high, then this means that there is a significant differences between the neighboring pixel intensity. For homogeneity, it reflects the proximity distribution within the GLCM to its diagonal. So in higher values of the homogeneity, this means that there is a concentration of elements along the diagonal, and this can indicate that we have a more uniform texture. The entropy quantifies the randomness. So high entropy means more complex and less predictable texture, and there is a great variability in the pixel intensity distribution. The correlation is the linear relationship between pairs of pixels. Higher correlations means there is more predictable texture within the image. Dissimilarity calculates the average disparity in intensity between adjacent pixels. And if you have higher dissimilarity, this suggests that you have great diversity in the texture. Now you understand the meaning behind each feature, and once you find a higher value in that feature, you can interpret it. So if you have two images, one for a benign tumor and another for malignant tumor, and you got the homogeneity values between them, or the homogeneity values for the first image and the second image, you will compare which is higher. Let's assume that the benign is higher in the homogeneity value. So you can interpret that by saying the benign image has more concentration of the elements along the diagonal than the malignant one. And if you are dealing with the entropy, you may say that a higher entropy image, let's assume it's the benign one, is less predictable with respect to the texture compared to the malignant image. So if you got another image that you don't know if it's malignant or benign, simply the system can discriminate between both of them based on the homogeneity, entropy, or correlation. Once the system finds a pattern of these features, it can decide that it's benign or malignant. Let's move to the equations. These are the corresponding equations for the different GLCM features, and we are going to use these functions using a hand calculation example so you'll understand the meaning of each symbol. Again, this is an interpretation summary if you got a high value and low value for the different measures. For example, the homogeneity, if you have a high value, then the texture is concentrated around diagonal, and this can say it's uniform texture, while at low value, it can indicate this uniformity. For the correlation, if you have high value, it's predictable texture or strong relationship, while for low value, it's weak relationship or less predictable, and so on for other features. Now let's back to our calculations. Let's start by calculating the energy. If you notice, the formulas are summations, and there are NCs for I, J, and there is a high value here, G, and there is P of I, J. What is the meaning of each of them? Simply, I, J are NCs, and G is the number of gray levels which is in our case n equals 4, and the p of ij is a pixel value as a location of I and j. So 0, p of 0 and 0 is equal 0 in this case, and it's worth noting that p means probability or the normalized GLCM value, and normalization here means that after calculating the matrix, we need to divide it by a certain value to normalize it, such as the summation of the matrix. So the total summation of the matrix will be 1. And we mentioned earlier in the previous lecture the importance of normalization. So in normalization, simply, you don't need the values to be much higher than the range of other features so that the model can be able to discriminate between them and avoid any biasness towards a certain feature because it's higher range or long range. But in our example here, we will not normalize to avoid any floating calculations. It will be the same, but instead of using the original one, you will use the normalized version. So let's back to the energy. In energy, simply, you are squaring each value in the co-occurrence matrix and summing all of that together. So square each value, 0 square, 2 square, 0 square, loop on each value here, 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 until you reach the end, 1 square, 0 square, which are there, and sum all of that, you will get an energy value of 45. What about the contrast? The contrast is similar, summation, summation, but here the formula is different. I minus j square multiplied by the value or the normalized value. You are using normalization. I is the index, let's assume for x, and j for y. We are squaring the difference between them. And it doesn't matter if you start with I rows or columns, because by the end you will reach to all of the values and they are squared, so the difference and the negative value isn't important here. So 0 minus 0 squared multiplied by 0, 1 minus 0 squared multiplied by 2, 2 minus 0 squared multiplied by 0, and so on. What about this field? It's 0 minus 3 squared multiplied by 1, which is here. What about this field? It's 3 minus 2 squared multiplied by 3, which is here. Sum all of that together, you will find a contrast of 26. What about homogeneity? Homogeneity is here. So instead of multiplication, you are applying division and adding 1 here. So let's get this field. The numerator is the value, which is 4. The numerator is 2 minus 1 squared plus 1, which is here. What about this field? The numerator is 3. The denominator is 1 minus 2 squared plus 1, which is here. Do all of these calculations, and finally you will find a homogeneity value of 11.8. And the same for other features. Now we need to know how to code these features using Python for the symmetric and non-symmetric. Move to code number 7, GLCM features example. Here we imported NumPy for mathematical operations and manipulation. We define the same parameters, same example, and at the beginning of the code, we copied the same code that we discussed earlier for calculating the co-occurrence matrix by converting it to NumPy, printing it, calculating the n value, creating an empty co-matrix, converting the angle, and start to calculate and fill the co-occurrence matrix using 2 inner loops, and then we checked if it's symmetric or not and printed the co-occurrence matrix. Once we have the co-occurrence matrix, we can calculate the different feature. For example, the energy. The energy is the square of each field in the matrix and sum all of that together. So simply we can use co-matrix raised to the power of 2, and here NumPy will perform pairwise calculations and apply the power to each element, and finally sum all of these values together into a single value. The contrast, we have 2 loops. Find the difference between I and j, square it, and multiply by the corresponding co-matrix. Then add all the values together. To do that, we initiated a contrast value of 0, and once you get a value, increment it and add it to the earlier or the previous value. So if it's 0, and for example, let's say the current pixel value is 1, so the new value will be 1. For the second iteration, it will be incremented and a new value will be added, and so on until it completes the whole co-occurrence matrix to get the final contrast. Next is the homogeneity. Simply, it's a value over 1 plus the square of the difference between I and j. We did the same. Homogeneity is 0 as an initial value, and add the new value to the other value and store it in the same variable. For entropy, it's a co-occurrence matrix multiplied by the log of the value, if you refer to the formula here, and there is a minus sign here. So instead of adding, we are subtracting, and here we are ensuring that the value is above 0, as the log of 0 will raise a non-value or not a number. For the correlation, you will find the formula includes mu of I and mu of j, sigma of I and sigma of j, and they refer to the means and standard deviation respectively. So to calculate both of them, simply we will calculate the mean x and mean y, and here we are calculating the mean in the x direction and the mean in y direction, and then dividing by the total sum, so you can get the mean value because this is the sum, and here will be the mean. To calculate the standard deviation, simply do the same using the standard deviation formula, I minus the mean squared multiplied by the value. There's the standard deviation in x-axis for the rows, and there's the standard deviation for the columns. We need to square the result, so we squared the result to get the standard deviation. Using the mean values and standard deviation values, we can fill in the equation, I minus the mean, j minus the mean, multiplied by the value. All of that are divided by the standard deviations. Loop on each value, sum all of that together in the correlation, which is initiated by 0 value. You will get a final correlation value. For the dissimilarity, the formula is easy. Instead of using power, we are using absolute value here. So instead of using power, we change it to the absolute, and we have now the dissimilarity. Now we have the 6 features: energy, contrast, homogeneity, entropy, dissimilarity, and correlation. We also printed the total sum and mean and standard deviation values. All of these are rounded to 4 decimal points using the round function. After executing the code for the non-symmetric, you will get these results, and if you change the flag from false to true to get a symmetric, this will be the result. It worth noting again, if you are dealing with real images or real matrices or big matrices, you must and you are recommended to apply normalization. And that's what we are going to do in the following 2 scripts. As we did with the first order features, we need to do here with GLCM. We need to replace the example matrix with the cropped ROI image so that we can calculate the GLCM features from that ROI. Now let's move to script 8, GLCM features for 2D. And here we imported 4 packages or libraries: OS for file path operations, CV2 for image processing because we are going to read images, NumPy for math operations, and plot for plotting. In the previous code, we processed 2 things, calculated the co-occurrence matrix, and then the second step was to calculate the features. Here, we encapsulated each step in a function. The first function is called calculate GLCM co-occurrence matrix, and the second is called calculate GLCM features. In this function, we defined 3 primary parameters. The first argument is image, which is the matrix or the image. Distance, theta, is the angle. Symmetric is normal and ignore zeros. First, we calculated the n value. Then, we checked if the d value, which is passed to this function, is lower than 1, then there is an error. And if the value is more than n value or equal, then there is another error, because the distance should be between 1 and less than n value. Because if it's equal n, so each neighbor or target will be outside the boundaries. Then we created the co-occurrence matrix, started to iterate over each pixel, get the current location, skip if it's outside the boundary, and we added a condition here, check if it's outside the boundary, and we added a condition here if you need to ignore the zeros. So if the start value or the end value are zeros, then skip it. And I will mention the importance of this point and this block after a while. Here we incremented the co-occurrence matrix based on the values. After completing the iterations, it will check if it's symmetric and also if you need to apply normalization. If you need to apply normalization, in this case, we will divide by a certain value, which is the sum of the co-occurrence matrix. And here we added a very small value to avoid any division by 0. Assume that the whole co-occurrence matrix is 0. In this case, you are going to divide by 0, and this will raise an error. By the end of calculating and processing the co-occurrence matrix, use the return to return the calculated matrix. Now let's return to the importance of ignore zeros. Look at this image. You will see that this is the lever, which is here, and this is the background, which is here. This assumes that this is the lever. And we have a pixel here. And let's assume the target pixel is here. Just for explanation, like here. This is black. So if you got a relation between the background and the pixel value inside the lever, then you are mixing between them, the background and foreground, which is the lever. So in this case, we need to ignore any background pixels. So we need to check once the iteration has an initial or current pixel value as 0, which is the background, then ignore the pixel. We don't need any relationship between the pixel and a pixel on the lever. And the same if you got a pixel here and a pixel here. So also if the target one is 0, then ignore it. We don't any relationship between a pixel on the lever and a pixel on the background. Also the same here. If it's 0 and 0, then it's totally background, then ignore it. So to ignore these three cases, we will check if the end location or the start location, any of them is 0, then continue, ignore it. This will be happen only if you need to ignore the zeros, which has a default value here is true. And also normalization is true and symmetric false. Then there is another function called calculate GLCM features. It accepts the co-matrix and then starts to calculate the different features that we explained earlier in the previous code. And at the end, it will return a dictionary that contains the feature as keys and the values for the corresponding features. Now we have two functions encapsulated to be used later just by calling them and passing the correct arguments. To do that, we started to read the lever image and the corresponding segmentation. It checked if both of them exist. Then we read these two images as gray scale images, apply bitwise, and to get the ROI, got the grouped version. It checked if that grouped version not empty by checking the summation. If it's all zeros, then it's black background, then ignore it, or raise an exception in this case. We define the parameters, distance, theta, convert it to radians, symmetric false, apply normalization, and ignore zeros. Then we pass these parameters to the function and retrieve the co-matrix. We pass that co-matrix to the second function and got the features. At the end, we printed these features and rounded each of them to 4 decimal points. Then we plotted a figure with two subplots. The first subplot is the grouped ROI. The second subplot is the co-matrix. Once you execute the code, you will get this output. These are the corresponding features rounded to 4 decimal points. And if you didn't apply normalization, you will find a very large numbers in each field. And here is the grouped ROI. Here is the co-occurrence matrix with the ignorance of the background pixels. Mostly, the co-occurrence matrix will look like that. It's symmetric around the diagonal. So if you made a line around the diagonal here, you will find that it's symmetric around that region. And you can interpret that region based on the homogeneity, entropy, correlation values, and so on, as we mentioned in the interpretation table. And these are other co-occurrence matrices plots by changing the distance and angle. Simply, if you changes the angle from 0 to 45, the contrast will decrease and the homogeneity will increase. And in this case, you can refer to the interpretation summary as we noted. For example, the contrast decreased. So simply, you can say it's getting more smooth texture, and homogeneity increased slightly. So you can say by changing the angle, it's getting more homogeneous or uniform texture. Or you can do the same and compare using the same configurations between two images, one for a certain tumor and another for another tumor or normal, and compare it using the interpretation table. Let's raise a concern about this function. If you go through the calculation of the features here, you may notice that there are two loops here, similar to loops here, similar to loops here. You may say that, why don't we combine all of these calculations together so we can decrease the elapsed time to calculate the features or to loop through the whole matrix, especially if this matrix is big enough that necessitates doing that. Simply, you are correct. Assume that n is 1000 and here 1000, then you are applying 3 iterations, 1000 by 1000, and this will consume much time. You may not notice that in a simple matrix because you are dealing with 5 by 5 or 10 by 10, but if you have multiple images and each image is 512 or 1024 or more, this will take much time. So simply we can get rid of that by combining them in a single loop. So in code 9 GLCM features for TD optimized, we have optimized this matrix. Let's call it calculate GLCM features optimized. The energy is the same as here. It's calculating using NumPy, and they apply vectorization, and it's fast and better than using loops. But for others, we initiated the different values at the top of the code or before the loop. We initiated loops, and inside it, we added the contrast, homogeneity, the entropy, dissimilarity, mean values here, and we didn't add the standard deviation because the standard deviation depends on the mean, so we'll calculate it in another loop. After calculating all of that, we have now 4 features. There are 2 more remaining. We calculated the mean, calculated the standard deviation, and based on the mean and the standard deviation, we calculated the correlation. Now, 1 more remaining, which is energy, calculated at the top. Now we have 6 features. So instead of using 1, 2, 3, 4, 5, 6, 7 loops, we decrease them only to 3 loops. So it will be much faster than the original one. Again, we return them as a dictionary, and to use that, we will update the calling here. Instead of calculate GLCM feature, it will be calculate GLCM features optimized. And the rest of the code is similar to what we described. Now let's move to a package called scikit-image, and this package implements the GLCM inside it, so we can also validate our results with their results and check that both are the same. So go to script number 10, GLCM features for 2D, import the packages, and import one more called scikit-image. There is a class there called feature. There are 2 functions, Gray-Level Co-matrix and the Gray-Level Co-props. This will calculate the co-matrix, and this will calculate the features. Do the same by reading the images, applying bitwise and bounding reg to get the cropped version. Check if it's not background only. Define the parameters, find the n value, and then call the function co-matrix, pass the input image, pass the distance, pass the angle, the levels, which is n, its metric, its norm or not, will return the co-matrix. Using the Gray-Level Co-props to get these features, contrast, correlation, energy, homogeneity, and ASM. Then we printed the features rounded to 4 decimal points, and we did the same plotting, the image, and the co-matrix. If you executed the code, this is our implementation. This is out of the scikit-image package. The energy is similar to their GLCM. The contrast here, like here. The homogeneity is here. The entropy, the correlation is here. And they don't have implementation for dissimilarity and entropy. And it's worth noting that their implementation for energy and ASM value are different, while in the lecture we define both are the same. So to get the energy or ASM from the package, you can use the ASM value. Now we need to proceed with the 3D volume, similar to what we did with the first 2 other features. But here, instead of calculating the features for each image or each frame in the volume, here we need the spatial information as a volume between the neighbors, whether they are in the same frame or the cascaded frames. So the processing here is different. So for a 3D volume, instead of using only XY axis, we are accessing a volume with XY and Z axis. XY in the same image or the same frame, Z in another frame. So instead of dealing with X target, Y target, we will get a new parameter. It's called Z target. And to construct the formulas as we did with the 2D, we can use the spherical coordinates. And in spherical coordinates, we have a point P, which has an angle phi with the z-axis and an angle theta with x-axis. And the angle here comes after the projection of P on the xy plane in the Q point. So simply what we need here is the projection of the point P along each axis, x, y, and z. So let's start by the z-axis because it's the simplest one. There is an angle phi here, so the projection of P along the z-axis is P cosine phi, which is here. So z target will be z current plus the round of d multiplied by cosine phi. Now let's get x target and y target. If this is cosine, because it's the angle between B and Z, the other direction or the other plane, xy, will be sine. So the projection Q here will be sine phi. So in x target and y target, you will see that sine phi is attached to each of them. What's after? We have an angle. And this angle is the angle between the projected Q and the x-axis. So the projection of Q on the x-axis will be cosine theta. So it's cosine theta. While on y will be the other angle will be sine theta. And we multiply it by d. Now x target will be multiplication of two angles. The same for y target. These are the three formulas. Let's assume that we are dealing with a single angle, because in the predefined parameters, we will say that we need an angle of 45 or 90 or 135 and so on. So in this case, theta will equal to phi. Substitute by each phi with the value of theta here, here, and here. So the final three formulas will be like that. Before moving to the script, let's raise an issue that may happen during your code. If you are dealing with these three images at top, and I asked you to find the neighbor to this pixel, which is here at distance 1, and let's assume any angle. So you may say, let's assume angle of 0. So I will use the three formulas to calculate the neighbor. So it may be here. And for the second slice or frame, it may be here. What happened? If you notice that the height of each of the three images are different. So if you are asked that there is a pixel here, it will be outside the boundary of others. And the same here, it will be outside the boundary of others. And this error or concern will be raised if the grouped images are not equal in sizes. And this may happen. So what is the solution? Simply apply padding to unify the shapes. Get the largest width, get the largest height, pad the other images to be in the center with that maximum height and width. So instead of using that height, we will add a black region here and a black region here, like what we did in this image. And the same for this one. One more thing, once we get the start location and the end location, or the current and the target based on the three formulas, we will end up with two pixel values. One for the current with the location x current, y current, and z current, and one for the target x current, y target, and z target. And hence, we will also refer to a 2D co-occurrence matrix, n by n. What about the number of frames? For most cases, the number of frames will not exceed the x and y axis. For example, 512 by 512 by 10 or 12 or 512 frames in original images. But in rare cases, or if you need to be more generic, you can construct the co-occurrence matrix based on the maximum between n and the number of frames. However, in our script, we are going to use n by n. So go to script 11's GLCM features for 3D optimized. You will find a function called calculate GLCM co-occurrence matrix 3D. It differs from 2D or the one we illustrated. It accepts the volume instead of the image. We defined here n, minimum and maximum, and increment 1. We got the number of slices, and we will use that to check if d is greater than the number of slices, then raise an error, because if it's greater, it will be outside the boundary of the number of frames. Create the co-occurrence matrix and initiate it with zeros. Start by looping on each pixel of the volume. Get the start location. Get the target location using the 3 formulas. Check if you are inside the boundaries. If so, then continue. If not, skip to the next pixel. If the start location and or the end location are zeros, then ignore and continue if you are turning this flag to true. Then get the start pixel and end pixel and subtract the min from both of them to deal with matrices or volumes that doesn't start with 0. Then increment the field. Check if it's symmetric, then add a transpose to the original and store it in the co-matrix. If it's normalized, then divide by the summation. And here we are adding a small value. So we can add a comment here as a reminder that this value is to avoid division by 0. Then return the co-occurrence matrix. Now this function accepts the volume with the different arguments and returns the co-occurrence matrix in 2D. Then we will use the same constructed GLCM features function from earlier codes that accepts the co-occurrence matrix and returns the features as a dictionary. Here the code, we defined the paths for the frames, 3 frames and 3 frames here. We defined the arguments, distance 1, theta, converted to radians, is symmetric, is normalization, apply normalization or not, and ignore zeros. And instead of manipulating the volume, here we constructed another function called readVolume that accepts the paths for images and segmentations, and it should return a cropped volume after padding and unifying the width and height for each frame. Then we will take it and get the co-occurrence matrix and calculate the different features, print the features on the console, round it to 4 decimal points. Inside this function, it will create a volume list as initiated as empty list, loop on each frame, apply the same processing, read the frame, apply ROI, group it, check if it's not empty, and append it to the volume. Next, we will find the max width and the max height along the frames or the grouped ROIs. Then we need to determine how much we need to increase in as padding horizontally and vertically. Simply subtract the current shape, width or height from the max width or height respectively. You will get the delta divided by 2 to get the left padding. Subtract that from the delta width to get the remaining right padding. We do the same for top and bottom. The padding value will be 0 as black. After padding, replace the original ROI or the grouped ROI with the padded one. After completing the loop on all of the frames, convert it to a NumPy volume or matrix and return it so it can be used later in this function. Now, if I executed the code multiple times with different distances, D1, D2, and D3, for D1 and D2 you will get results, but for D equal to 3, it will raise an error because it's equal or higher the number of frames or slices. For D1 and D2, you will get these corresponding results for different features. You may notice that if you increase the distance, you may get a decrease in the entropy, a decrease in the correlation, an increase in the dissimilarity, and based on the interpretation summary table, you can simply interpret the differences between increasing distance or changing the angle or comparing it between multiple volumes and write your interpretation. So in this lecture, we have covered the GLCM and how to calculate the GLCM features by first constructing the co-occurrence matrix, and based on that co-occurrence matrix, you can gain the features such as entropy and dissimilarity. You now can interpret the different features if they are high or low, comparing between different examples or images. We moved from handling simple matrices to dealing with images and then to volumes. You can combine the first order features and second order features GLCM and other features into a whole features dictionary or a file and use it later in the classification, so that the model can discriminate between the tumor types or the grades of a tumor, or being normal or malignant or benign, and so on. We also covered hand calculations, and you can validate these hand calculations for simple matrices using scripts. So if you get two examples of two matrices, one is assumed for a normal and one is assumed for a tumor, you can simply calculate the feature for both of them, and using the interpretation table, you can write your interpretations.